In this lesson, we're going to build upon our idea of sequences and start talking about series. Now, in the previous section, we talked a lot about sequences, and sequences is just basically a list of values that are in a particular defined order. Now, when we talk about series, that is when we add up all of those values that are in the sequence. So this is what it looks like when we write it out in mathematical notation. If I have a sequence AN and I sum all of those terms, that's called a series. Now, we have something that's called a partial sum, which means instead of adding up the infinite values in that sequence, the partial sum is where we go out only to a certain term and we add those up. So that notation looks like this. So the notation is SK, where K is some value, and that will be the term that we stop at. So for example, if I said K is 5, that means we would take the first term, the second term, the third term, the fourth term, and the fifth term and add them all up. Now, the idea of the partial sums is very important because that's going to help us determine on whether or not the series converges or diverges. If the limit of the partial sums approaches some value and it converges, then the series will converge. If the limit of the partial sums diverges and it doesn't approach some value, then the series is going to diverge. Let's look at our first example. For each of the following series, use the sequence of the partial sums to determine whether the series converges or diverges. So we're going to look at this series first. Now, if we list out the terms of the sequence, if I plug in n is 1, n is 2, n is 3, and I keep doing that, the first few terms looks like this when I list them all out. So this is the sequence. As soon as I start adding them up, that's when it becomes a series. Now, if I want to look at the partial sums to help me determine if this is going to converge or diverge, I'm just going to look at S1, which is just adding up everything up to the first term, which is just a half. S2 is adding the first two terms, so I add 1/2 and 2/3 to get 7/6, which is approximately 1.2. S3 is when I take the first three terms and add them, and that will give me 23/12, which is approximately 1.9. S4 is the first four terms added up, and when I add those up, I get approximately 2.7. Now, if I start looking at the pattern of the partial sums, this is why the partial sums is important. If the limit of the partial sums converge, then the series converges. If the limit of the partial sums doesn't converge, then the series diverges. If you notice here, if I look at the limit, S1 gives me 0.5, S2 gives me 1.2, S3 gives me 1.9, and S4 gives me 2.7. And if I continue that pattern, notice that these values are growing and growing and growing, and they're not approaching a specific value. So the limit of the partial sums does not converge. This is just going to continue to grow and grow and grow. So since the limit of the partial sums diverges, then we would say the series diverges. Let's look at part B. If I list out the terms of the sequence, if I plug in 1, plug in 2, plug in 3, etc., I get these terms. It bounces back and forth between -1 and 1. Now, if I look at the sums, if I look at the partial sum for the first term, that will just give me -1. The second partial sum will give me 0 because I add the first two terms. S3 is when I add the first three terms, so that will give me -1. And if you notice this pattern, the sums or the partial sums are going to bounce back and forth between -1 and 0. which means that the limit of the partial sums doesn't exist. So we can say, since the limit of the partial sums diverges, then the series diverges. Okay, let's look at the third example. If I list out my terms for the sequence n over n times n plus 1, I get a half, 1/6, 1/12, 1/20, and 1/30. So then when I start adding them up, S1 will give me a half. That's the sum of the first term, which is just a half. Then S2 is the sum of the first two terms. So if I add 1/2 and 1/6, it gives me 2/3, which is 0.6 repeating. Then if I get S3, that means I add up the first three terms, and that gives me 3/4, which is 0.75. And then S4 gives me 4/5, which is 0.8. If you continue this pattern, you're going to see that the limit of the partial sums gets closer and closer to 1. So, since the limit of the partial sums approach 1, we can say that the series is equal to 1. So this converges. Now, there's a pretty famous series called the Harmonic Series, and this is what it looks like. You just take the sequence 1 over n and add it from n equals 1 to infinity. And when you add up those terms, it actually diverges. When you look at that, you think, well, the value of n gets bigger and bigger, so the fractions get smaller. The sequence will converge, but you'll notice that the series does not. So if we look at the terms, we have 1, 1/2, 1/3, 1/4, etc. Add 1 plus 1/2, so that's 1.5. S3 is what I get when I take 1, 1/2, and 1/3, which ends up being 2.83 repeating. S4 gives me 3.83. S5 gives me 3.283. And if you keep looking at this pattern, the sums are getting bigger and bigger and bigger. So even though the sequence 1 over n converges as n goes to infinity, the sum or the series does not. Because the limit of the partial sums diverges, we can say that the series diverges. So now let's look at the algebraic properties of converging series. And the key to this is to know that the series AN and BN both have to converge for these to hold true. If AN and BN are convergent series, then if I have the sum of AN and BN, I can split them up into two separate sums. Same thing goes for the difference. That's called the difference rule. I can split it up by subtraction. Again, I have to stress that you have to know for sure that these individual series converge. And then if you have a convergent series with a constant in front, you can just pull that constant out in front. So using the algebraic properties of convergent series, we're going to find what the series is equivalent to. Now, I know that 1 over n times n plus 1 converges because we just did that in the previous example. We said that that converged to 1. So I know this series converges for sure. Now, let's check to see if this series converges. So think of this as my A and this is my B. I'm looking to see if they converge, and if they do, then I can add them up separately, like in the property up here. Okay, so if I know each of these separately converge, then the series of the sum of those is going to be the sum of the individual series. So looking at this series here, if I write out my terms, I get 1, 1/2, 1/4, 1/8, 1/16, etc. So I wrote out a bunch of the terms. So, and then I started calculating the partial sums. The first partial sum was 1, the second partial sum was 1.2, etc. If you notice, the limit of the partial sums approaches 4. It's getting closer and closer to 4. So that tells me that this series converges, which tells me that the series is equivalent to 4. Because I know that this series converges and this series converges, I know I can add them separately to evaluate the sum. So if I take 3 times this was 1. So this series converged to 1, and when I multiply that by 3, I get 3. And this series we just found was 4, so when I add them up, the sum of those two would be 7. So you can use these rules here as long as you're certain that each of those individual series converges. The next series that we're going to talk about that's fairly common is the geometric series. And so the geometric series looks like this. So we would add up all the terms of this sequence AR to the n minus 1. Now, if your common ratio, your R, if you take the absolute value of that and it's less than 1, then we know that this series is going to converge. And it's going to converge to the value of A over 1 minus R. So this is our formula for finding the value that this converges to. Now, if the absolute value of R, your ratio, your common ratio, is greater than or equal to 1, then the series is going to diverge. So let's look at a couple of examples of this. So determine whether each of the following geometric series converges or diverges, and if it converges, find the sum. So using some algebra manipulation, I'm going to rewrite this sum as -3 squared times -3 to the n minus 1. Now, we need to rewrite it so that we have it in this form, so we can identify the values of A and R. So now, if I use my knowledge of exponents and algebra, I can rearrange this expression to get it in the form that we need so that we can identify the values of A and R. So I'm going to break up -3 to the n plus 1 as -3 squared times -3 to the power of n minus 1. And then I'm just going to carry over the 4 to the n minus 1. When I simplify this, the -3 squared gives me 9. And since my powers are the same here and here, I can rewrite this as -3/4 all raised to the power of n minus 1. So now I have it in a form where I can identify A and R. A is 9 and R is -3/4. So when I take the absolute value of R, that's definitely less than 1, so we know that it converges. Now we can use the formula A over 1 minus R to determine what it converges to. So here's my A on top, 1 minus my R, which is -3/4. And when we simplify that, we get 36 over 7. Now, if I look at the second example, or part B, I'm going to rewrite, using the same trick, I'm going to rewrite e to the 2n by pulling out an e squared, which would leave this as n minus 1 instead of n. Now it's in the form that I can identify my values of A and R. A would be e squared and R would be e squared. And because R is greater than or equal to 1, this series is going to diverge. Now, one of the neat things about the geometric series is we can use that to find fractions for repeating decimals. So something that you may or may not be aware of is there's a pattern with repeating decimals as far as coming up with a fraction to represent those repeating decimals. So if I wanted to find, for example, the fraction that represents 0.121212 repeating over and over and over again, the part that's repeating is 1, 2. Because there are 2 digits, I would take the part that's repeating, which is 1, 2, and I would divide it by 2 9s, because there's 2 digits here in the part that's repeating. You would divide by 2 9s, so I would take 9, 9. Now, when I hit enter, it's going to give me the decimal 1, 2, 1, 2, 1, 2, 1, 2 repeating. You can try this with a few different numbers. Let's say I wanted to find the decimal Or let's say I wanted to find the fraction value for 0.123, 123, 123 repeating. So I would take 123, that's the part that's repeating, and I would divide it now this time by 3 nines because 3 digits are repeating. So when I hit enter, I get 0.123, 123, 123 repeating. That is why if I take 3 divided by 9, I get 0.3333. Now, this is kind of a neat thing to know if you haven't already seen this before. But now, using the geometric series, we can prove that this is the case. So, looking at this example, I want to show, using a geometric series, we're going to write 3.26 repeating as a fraction. So I'm going to separate the whole number, and I just want to show that 0.262626 repeating is 26 over 99. And then we add it to the 3, of course, and we get 3 and 26 over 99. I'm going to take the 0.262626 repeating, and I'm going to break it up into the repeating parts. So this 26 here, this 26 here is the same as saying 26 hundredths. 0.26, that's 26 over 100. If I take the next 26 that's repeating and I add it to what I already have split up, that's 0.0026. Then I add it to get the next 26 here, I add it to 0.000026. So ignoring the whole number 3, if we just look at this part here, the repeating part, this is actually the sum of a geometric sequence, and I can write it as 0.26 times 1 over 10 to the n minus 1. Now, because this is a geometric series, and it's in the form that we can identify the a and the r, this is my a, and 1/10 is my r, and since 1/10 is less than 1, we know that the series converges. So I'm going to take my a over 1 minus r. So that's 1 minus 1/10. And when we clean that up, we get the part that's repeating is 26 over 99. And then, of course, you add in the 3, which I skipped that part because I was focused on this. But this part here is 26 over 99. And then, of course, you still have to add it to the 3. So 3.26 repeating as a fraction would be 3 and 26 over 99. Okay, the last topic we're going to talk about in this lesson is called telescoping series. And that's when most of the terms are going to cancel when we're looking at the partial sums, leaving only a few terms that are left. So here's an example so you can grasp what we're talking about here about things canceling. If I look at the terms of this series, if I plug in 1, I'm going to get cosine of 1 minus cosine of a half. Then the second term is going to be cosine of a half minus cosine third, because I bumped n equals 1 up to n equals 2. So 2 goes here, and I have 2 plus 1, which is 3 down here. If we continue that pattern, notice that the bottom number in the second term just increases by 1 in the denominator. So these are all my terms. Now, when I start finding the sums and I start adding them up, I have a minus cosine and a half plus a cosine of a half here. So these disappear and I'm left with cosine 1 minus cosine a third. When I find S3, that means I'm adding up all of these, which now means the cosine 1/3 disappear and I'm left with cosine 1 minus cosine to the 4th. So then that pattern continues. And so what's going to happen is, to find your nth sum, you're going to be left with the first and the last term of that sum, because everything in between is going to end up canceling out. So to find the nth sum, we're going to end up with cosine 1 minus cosine of 1 over n plus 1. Now, if we look as the limit approaches infinity, this is just a constant, so that's not going to change anything. But the inside here is going to approach 0. And when I take the cosine of 0, I get 1. So when we take the limit as n goes to infinity, we get cosine of 1 minus 1. Therefore, since the limit of the sums exists and it converges, then the series is going to be equivalent to cosine 1 minus 1. So when you're dealing with the telescoping series, most of the terms are going to cancel and you're just going to be left with a few terms, which makes it a little bit easier to figure out what your series is equivalent to.